Right. Welcome to worksheet Stoichiometry Problems 1.5. For this, you will need a calculator. You also will need a periodic table per usual. And on this one, you are going to need a polyatomic ion sheet later in the worksheet. So if you want to grab those things, get ready. Again, as these living answer keys go, I would make sure that you are feeling good. Watch a problem or two and then pause the program. And you want to try to answer them by yourselves and then just let me kind of corroborate what you're saying as you go. So make sure you're trying some of these. Pause the program whenever you would like and see if you can't get this going. All right, first thing, whenever we look at any stoichiometry problem, as it says here in the instructions, be sure to balance the equations first. So I would have you first try to balance this equation. Perfect. All right, so if you balance it, you're going to get 4, 3, 2. The next hardest part about stoichiometry is knowing what to do. So what we're going to do here, we're going to read the question. It says, what mass of iron is needed? So I'm going to say, I want to know grams of that. What mass of iron is needed to produce 3 grams of iron oxide? So I want to end up with 3.00 grams of iron oxide. So the first thing we're going to do, we cannot just say, hey, look, it's a 2 to 4. I only need 6 grams of that. No, you can't do that because we can't move around in grams. We can only move around in moles. So the first thing I need to do is I need to take what I have and I need to find moles of that. So if I want moles of iron oxide, I want to take the mass of the iron oxide over the formula weight of the iron oxide. Now, how did I get 160? I want 2 irons at 56 and 3 oxygens at 16 each. Okay, add that all together and that gets you 160. When you multiply that, you get 0.019 moles of iron oxide. Perfect. Now, once we have moles, we can go anywhere. We could go here, we could go here, we can answer anything. But the question asks, what mass of iron is needed? So I'm going to follow my mole ratio. This is a 2 to 4 ratio, 2 to 4. So what am I going to do with this number if it's a 2 to 4 ratio? We're going to double it. Times 2. We're getting larger by 2. 2 to 4. Getting bigger. Let's double it. When we do that, you get 0.038 moles. Oops, sorry. And now it's moles of iron. By going ahead and doubling that, you have now moved it to moles of iron. The question, though, did not ask for moles of iron. It asked for mass of iron. So I'm going to set that equal to X over the formula weight of iron only, which is 56. To solve this, you multiply these two problems together, and we get 2.13 grams of iron. Suggest you pause the program and try number 2. Make sure you balance it first. All right, so once you've balanced the equation, we're looking here. And the question says, how many grams of copper oxide, so my question is here, how many grams of copper oxide are needed to produce 27.39 grams of oxygen gas? So the first thing I have is I need to take what I have and I need to put it into moles. So I'm going to take the 27.39 and I'm going to divide it by the formula weight. Now be very careful. Common mistake. Coefficients do not affect formula weight. Okay? The formula weight of copper is always 64 no matter how many you have. So while coefficients do not affect formula weight, however, subscripts do. So if I have 2 oxygens stuck together, they're each 16. The formula weight of O2 itself here is going to be 32. You do that math and you get yourself 0.86 moles of O2. Get rid of some of this clutter. Oh dear. You see nothing. Oh dear. Alright. What is going on? So what we're going to do is we are going to take this number here. This is a 1 to 2. 1 to 2 ratio. So all I need to do is, if it's a 1 to 2 ratio, I'm going to multiply it by 2. Once you get that, you have 1.72 moles, and now it is copper oxide, because now we've reached moles of this. Moles equal mass over formula weight, so if I have moles of copper oxide and I want mass of copper oxide, I'm going to put it over the formula weight of copper oxide, which 1 copper and 1 oxygen added together makes 80. Okay. Again, coefficients do not affect formula weight, so that's just 80. Multiply it together, we should get 137.6 grams. All right, I'd have you pause the program, see if you can't do 3 and 4. Number 3 is special because number 3 is already, oh, nope, that's number 4. Number 3 needs to be balanced, sorry. Okay, now we are balanced. Reading the question, what mass of chlorine gas, question mark, is needed to react completely with 34.65 grams of potassium iodide? Again, take what you know, put it into moles. If I have 34.65 grams of potassium iodide, I divide it by the formula weight of potassium iodide. 1 potassium, 1 iodine gets me 166 for a formula weight. If you divide that out, we get 0.21 moles of potassium iodide. Now, I'd like for you to try to do the ratio. What am I going to do with my moles of potassium iodide to get me moles of Cl2? Awesome. So, we are going from here to here. This is a 2 to 1 ratio. Am I getting bigger or smaller? I'm getting smaller, so I need to divide by 2. So my sig figs get a little off here, but I feel like I need the 3. I don't know. You could have this be 0.11 if you would like. It's up to you. If I have moles of chlorine gas and I want mass of chlorine gas, I put it over the formula of chlorine gas. Again, Cl2. Subscripts affect formula weight, coefficients do not. So we need 70 for our formula weight. Multiply those things together, and you get about 7.35 grams of chlorine. If you use 0.11 moles, you might have a little bit of a different number, but that's okay. All right, number 4 is already balanced. Let's see if you can pick it up from here. What mass of water is produced if I start with 90.45 grams of sulfuric acid? Take what I have, 90.45, divided by the formula weight of 2 H's, 1 S, and 4 O's gets me 98. If you do that division, you get 0.92 moles of H2SO4. Now, what am I going to do with this ratio? This is very easy. All of these are 1 to 1 to 1, so I'm not going to do anything. And I have the exact same number of moles of water. Again, that's because we're going from here to here. Again, it wants mass, not moles of water. So I'm going to go X over 18, formula to water, and you end up with 16.56 grams of H2O. All right. Last one, I would say, before we do some other different kinds, pause the program, see if you can't figure out what we've got going on here. Balance it. All right. Once you've balanced it, let's take a look. This is what we should be seeing. Reading the question, what mass of pure iron is needed to produce 12.00 grams of iron 3 sulfate? Okay, so I take what I know, I put it into moles. I'm going to do 12 divided by, okay, we're looking for moles of iron 3 sulfate. So this one's tough. 2 irons, 3 sulfurs, and 12 oxygens. So it's a big number. We got 400 here. 12 divided by 400 is going to give me 0.03 moles of the iron 3 sulfate. Now, let's take a look. We are here, and this is a coefficient of 1 to 2. 1 to 2. So what am I going to do with this mole? I'm going to double it. Very good. Okay, and we're looking at 0.06 moles of iron. And again, it asks for mass of iron, so I'm going to go X over the formula weight of iron, 3.36 grams. All right, now we're just going to try a different kind here. You're going to have to be able to write and balance the following reactions. Then we're going to answer the stoichiometry problems. So, you probably will want to, I guess you don't need, oh yes you do. You will need a polyatomic ion sheet as you get along. Pure aluminum. So we're just going to say Al. Pure aluminum metal reacts with oxygen gas. Remember, oxygen gas is always O2 to produce aluminum oxide. Now, we can't just write AlO, okay? Because that is not neutral. So if you ever want to do that, please don't. Okay? Let's figure out what we are going to do instead. Aluminum on the periodic table is in group 3, so it's a +3. Oxygen is group 6, so it's a -2. What can I do to have both of these be neutral? What would my neutral formula be? Al2O3. Okay, they're both going to go into positive and -6. Beautiful. I'd pause the program, see if you can't balance this. All right, once you balance it, it should look a little bit like that. Now let's read the problem because it's going to be very, kind of throwing a curveball at you. How many moles of aluminum oxide, I'm not grams though, I want moles, of aluminum oxide will be produced if I start with 23.50 grams of pure aluminum? So I want moles of aluminum. I have mass of aluminum over the formula weight of 1 aluminum. Remember, coefficients do not affect formula weight. Do that math and you get 0.87 moles of aluminum. Be very careful. We have this. This is a 4:2 ratio, 4:2, 4:2, 4:2. What am I going to do with this number? Good. Divide it by 2, and you get 0.43. Again, I stick my extra fig on there. Sorry, you could say 0.44 moles of aluminum oxide. Now, do I want to go any further? What did the question ask? How many moles of aluminum oxide? Do we have the right answer? You bet we do. Moles of aluminum oxide. Good. So you stop right there. I'd have you try to write and balance this next equation and then answer this problem all by yourself. All right. Calcium chloride +2 -1. Calcium chloride is CaCl2. Reacts with potassium fluoride. Potassium's a +1, fluorine's a -1. We're looking that up off the periodic table here. So reacts with is a plus. 1 of each. To produce calcium fluoride, +2 -1. So in order to write this neutrally, we have to say CaF2 and plus potassium chloride, +1 -1. So that's just going to be KCl. Now, the next thing you need to do is make sure you can balance this. Let's do it together. I see 1 Ca, 1 Ca. 2 Cl's. Oh no, I only see 1 Cl, so I'm going to put a 2 here. Now that gives me 2 K's, however, so I'm going to put a 2 here. Now I see 2 F's, 2 F's. We are balanced. Question says, what mass of calcium fluoride, so we're back to finding grams, is produced when 90 grams of potassium fluoride is reacted? Perfect. So, first thing we want to do is we want to take our 90 grams divided by the formula weight of potassium fluoride, which happens to be 58. That gives me 1.55 moles of potassium fluoride. Now, let's take a look at where we're going. We are here, potassium fluoride, calcium fluoride. 2-to-1 ratio. Very good. Divide it by 2. And you get 0.78 moles of calcium fluoride. It doesn't want moles of calcium fluoride. It would like mass of calcium fluoride. So put it over X over the formula weight of 1 calcium and 2 fluorines. Multiply that together and you get yourself 60.84 grams of calcium fluoride. All right, last one I have you try by yourself. See if you can't write it, balance it, and then tell me what mass of potassium hydroxide will be produced from 40 grams of potassium. All right, let's write this together. Potassium metal is K. Reacts with water, which is H2O, to produce potassium hydroxide plus 1. We know hydroxide is an OH minus 1. Hydrogen gas is always H2. Okay, so let's say potassium hydroxide we know is just KOH, and hydrogen gas is H2. In order to balance this, we need 2, 2, 2, and then it's by itself. Pause the program and answer the question. Question says, what mass of potassium hydroxide will be produced from 45 grams of potassium? Do 45 divided by the mass of 1 potassium. Again, formula weight is not affected by a coefficient. When you do that math, you get 1.15 moles of potassium. What is the ratio from potassium to potassium hydroxide? Potassium to potassium hydroxide, that's a 2-to-2 or a 1-to-1, so I'm going to keep that number the same. Now that's moles of KOH. The question, though, isn't how many moles of KOH, it's the mass of KOH, so X over the formula weight of KOH. Multiplies those together, and you get a final answer. Hopefully you're feeling good on some of these questions. Bring any questions you have into class.